let's take a look at our last gas law. This one is called the ideal gas law. So what exactly is an ideal gas? Essentially, an ideal gas is a hypothetical gas, and we basically say that it obeys all of the gas laws under perfect conditions, and it follows all of those laws perfectly. Now, we consider an ideal gas as one that does not condense into a liquid when cooled. And when we were to look at graphs of temperature, pressure, and volume, they would be perfectly straight lines. There would be no changes in those graphs. So we also need to look at the kinetic molecular assumption for ideal gases. Now, the kinetic molecular assumption is saying that we have the movement of molecules in our gases. So that's what kinetic means. It's kinetic energy or the movement. Okay, so we would say that in an ideal gas, that gas molecules are very, very far apart in comparison to their size. We would say that gas molecules are in constant random motion, and that motion is in a straight line. Okay, and that is due to the fact that there's no forces existing between our gas molecules. And the third point with the kinetic molecular assumption is that gas molecules undergo perfectly elastic collisions where no energy is lost. Now, if we were to look at a real gas, we would see that at high pressures, for the first statement here, we would see that for high pressures, the molecules are forced really close together, and their size all of a sudden does become significant. So the empty space available is less than their size. So we see that under really high pressures that this first assumption with real gases isn't always true. The second assumption with real gases, we see that when the temperature really decreases very, very, very low, it depends on the gas, we see that molecules slow down so much that eventually the intermolecular attractions cause those gas molecules to stick together and they become a liquid. So they do condense and create a liquid. So they aren't in constant random straight line motion and no forces exist between them. Well, that doesn't always happen if we cool it really low. So real gases, this assumption doesn't always come true either. Now with number 3, it says they go under perfectly elastic collisions. Okay, we consider in real gases, we have molecules that are more like soft spheres. They change shape during a collision and rebound, and so they makes the process occur a little slow, and it means that the pressure of the gas is a little bit less than what an ideal gas is. So it's not perfectly elastic collisions. They kind of morph shape a little bit, and the reactions are a little bit slower than an ideal gas, as well as the pressure becomes a little bit less. However, in order to do any sort of calculations for gases, we need to have these assumptions to follow. Now, our ideal gas law looks like this. It's PV equals nRT. And another way to remember it is PERV-NERT. That's one that sticks with many students. So we have pressure volume. N is the number of moles. R is a universal gas constant, which I'll mention in a second here. And we have our temperature. Now, this is super important that your temperature in this calculation is in kelvins. If it wasn't important in your other calculations with your other gas laws, which I encourage you to change all of your temperature values to be in kelvins, it is vital to this calculation that you convert your temperature into kelvins. And the reason being is our universal gas constant has a unit of kelvins as part of its overall unit. So when we look at R, we have 8.314, which is the universal gas constant, and the units are kilopascals times liters over moles times kelvins. Now again, because we have our unit in Kelvin for our universal gas constant, we must be calculating our temperature in kelvins. So for all of your other gas laws, it's just good practice to convert all of your temperatures from centigrade to kelvins. So we have this magical formula, which we will learn how to use in a minute here. So let's take a look at an example. I just am going to jot down our general formula here, PV equals nRT. And I'll put in the top corner that R is equal to 8.314. All right, and as long as you have an idea of what the units of R are, then you'll be okay to complete this just without writing the kilopascals times liters over moles times Kelvin. That's a lot of writing, so you can just write it down as 8.314. Now, when we look at this, we are going to look at the volume occupied by 0.78 grams of hydrogen at 22 degrees Celsius and 125 kilopascals. So let's begin to jot some of these numbers down. We have pressure of 125 kilopascals. Again, we need our units to be in kilopascals for the proper unit cancellation in this calculation. We are looking for the volume, so we're solving for volume. Our moles we can get from our mass value, but we do need to do a preliminary step to solve for moles. And R is equal to 8.314, and our temperature in this case is equal to 22 degrees Celsius. Again, we need to add our 273 degrees Kelvins because we need our temperatures to be in Kelvin. So this gives us 295 kelvins. Okay, so then when we start to solve for the number of moles, we are going to look at moles equals our mass over our molar mass. Now our mass is our 0.78 grams, and we have to remember that hydrogen gas is HH2. So when I look at my molar mass of hydrogen, it's 2 times our individual atomic mass, so we have 2 times 1.01 grams per mole, and that equals 2.02 grams per mole. So this equals 2.02 grams per mole. So to figure out the moles, we go 0.78 divided by 2.02, giving us 0.386 moles. So I'll just put that number down here for the number of moles, 0.386 moles. All right, so to solve for volume, we need to rearrange this formula to solve for V. Now because I have pressure times volume, I'm going to divide by P, and I'm going to get a formula that looks something like this, where volume equals nRT divided by P. I can start plugging my values in for this formula. I have 0.386 moles times by R, which is 8.314, times by T, which is 295 kelvins, divided by my pressure, which is 125 kilopascals. Oops. There we go. So when I plug all of my values in, if I can, I should leave my moles to the most digits, and if I do this on my calculator, I can do that by storing that value. So if I store that value, that's the best way. That way I'm only rounding one time in my calculation, which is the proper way to do that. So when I solve for this, I get my volume to equal 7.6 liters. All right, so again, this is a relatively simple formula to rearrange and to use, but there's some tricks that we need to remember, like converting our temperature to kelvins. Let's take a look at one more example here before you move on to an assignment or some additional practice questions. Again, we have PV equals nRT. Remembering that R is equal to 8.314. And this time we're looking for the mass of hydrogen. Now, again, we have hydrogen gas, so we have H2, and we're looking for mass. So in order to find mass, we probably need to look at solving for moles. Let's write down the other variables that we have. We have volume to be 3 liters. We have a pressure to equal 140 kPa. And we have a temperature being 20 degrees Celsius plus our 273 kelvins, giving us 293 kelvins. We can't forget about our R, which gives us 8.314. So when we rearrange our formula to solve for moles, I'm going to divide by RT in order to get N by itself. So I would get N equals PV divided by RT. So when I plug my values in for this formula, whoopsies, I get my pressure of 140 kilopascals times by my volume, which is 3 liters, divided by 8.314 times by my temperature of 293 kelvins. Again, if you plug this into your calculator, make sure you have brackets around this bottom section. The top section could be also important, but definitely this bottom section, so that when you divide by this, you're not dividing by 8.314, then multiplying by 293, you're dividing by this whole section. So when we go to plug that in, we have 140 times by 3 divided by 8.314 divided by 293 and divided by 293. So our moles is equal to 0.172 moles. Now because we're looking for mass, we have one more calculation to do. Mass is equal to moles times molar mass. And again, our molar mass of hydrogen gas is 2.02 grams per mole because we have 2 moles of it. So we get our moles of 0.172 moles times by our 2.02 grams per mole. We'll get a unit in grams. We get our value equaling 0.35 grams of hydrogen gas. So you can see how we can use a variety of ways or a variety of ways to rearrange this formula to solve for different variables. Please note that if you solve for mass, you're also using this formula to solve for moles, and we can go from mass to moles or moles to mass and still use this formula. Now, I would recommend going through some practice questions out of the textbook, or if you find some online, that's good too, prior to moving on to an assignment. Go back if you need to and take a look at both examples that we've gone through, and good luck.